Thank you so much, Attilia. It's brought back so many memories from the past, and thank you for your inspiring words as well. Thank you so much. So please feel free whenever you're ready. We'd love you to stay, but whenever you're ready, you can go. Thank you so much. So today I'd like to start off, I didn't realise that photograph was going to be up there, but I'd like to start off with the first presentation of the symposium, where I'd like to cover a brief history of the vanadium battery development here at UNSW. It's 40 years, so it's impossible to cover everything that we've done. So it'll be just some highlights of the work that has been done, acknowledging the people who have done it, who are here with us today. So, thank you. Oh, yes, please. Okay, so where did the original idea come from? And so many times I've been asked this question, what made you think of vanadium? Well, I've got to say that we didn't initially think of vanadium, but it all started with Martin Green, who I think everyone here would know Martin Green's work on photovoltaics, and he's been a pioneer and a champion of photovoltaics for so many years, and I think 50 years is his 50-year anniversary, so this is another important milestone in Martin's case for his 50 years, so congratulations, Martin. But he's started off with recognizing the importance of energy storage, long-duration energy storage for the future of photovoltaics and renewable energy. So he visited NASA many years ago, and NASA laboratories is where the idea of the flow battery started. And Larry Thaler, who I was very honored to have met many years ago, he came up with the idea of a flow battery, which had large tanks of electrolytes with 2 different redox couples, and his group went through and tested many different redox couples and selected iron and chromium on the basis of cost and availability. So I think it was around 1984, Martin had a student who happened to be a professional officer in industrial chemistry back then in the laboratory. And it was the same year that I had started as a lecturer in industrial chemistry as well. And he was doing his master's thesis on the iron chromium flow battery. So he was setting up his experiments, and he was running experiments, and he used to call me over every now and then. He wanted to discuss what was going on in his cell. And one of the things that he was highlighting at the time was the fact that the iron and chromium solutions were very quickly mixed through the membrane, and very quickly would lose capacity. So I was starting to talk about this subject with one of our other colleagues, Professor Bob Robbins, and the idea of using the same element on both sides came up. Bob Robbins at the time was working on vanadium. He was looking at extracting vanadium from various ores. And he said, Maria, vanadium exists in many different oxidation states. So we thought, okay, well, we went through the periodic table and looked at other possibilities. That was one of them. So we thought, okay, we'll have a look at that. But when we looked at the literature at the time, it seemed that vanadium wouldn't be a good choice, because NASA had considered it, but they rejected it on the basis of low solubility. You need to have a high concentration of ions in solution if you're going to have a flow battery. So it was low solubility was rejected, but also poor reversibility. In other words, the electrochemical reactions didn't reverse easily. So it didn't sound like a good option, but we thought, no, let's try it anyway. So that year, the next year, a couple of years later actually, I was very fortunate, I was so honored to have Elaine Sun nominate me as a supervisor of her honours thesis, because she was our star student at the time, about to get a university medal. So I was so honored to have been selected for her thesis. But I wanted to make sure that this is going to work. Yeah, I didn't want a failure. I didn't want the project to be a failure. So during the Christmas holidays, I did some quick experiments, and I thought, it looks like it's going to work. So anyway, Elaine started her thesis, and she was meticulous in her experiments and doing all these cyclovoltammetry experiments, which is one of the techniques that we use. But she found a big problem, that the reaction, as the literature had said, the reaction wasn't reversible. I can't see, I don't know if you can see a pointer. When you tried to reduce the V3 to V2, we couldn't see any reduction happening. And she'd come running into my office, Maria, it's not working, I can't get it to reduce. So we'd go into the laboratory, scratch the electrode, put it back in, and it would work. And then we realised that it was actually the way that the surface of the electrode was treated. It had to have defects on the surface, and by polishing it nicely, meticulously, that killed off all the active sites. So this was a major initial discovery, that it was the surface of the electrode that made it such an important, it was such an important feature of the reversibility. So she continued working, and she screened a whole lot of different electrolytes, acidic, basic electrolytes, and identified sulfuric acid as the best electrolyte. So we thought, okay, this is a good opportunity, now we can apply for grants. So I contacted Martin and Bob Robbins and Tony Fain, because we thought, okay, redox flow batteries, we need a membrane, that's a critical part of it. So Tony Fain was our specialist expert, world-renowned expert in membranes in the school. So we came together, applied for a grant, and we were fortunate. The first time we actually didn't get it, but the second time, after we included Elaine's experiments, we got the grant. So from then on, we were able to continue. So in fact, that first experiment, we published Elaine's results, 2 papers she got out of her thesis. And then soon after, once we got the grant, we were able to appoint various people, including Miron Richik, who was key to a lot of the early work that we were doing at the university at the time. Unfortunately, I couldn't contact him, so I would have loved to have had him here today. But he then put the cell together, and we were able to also find that even though the solubility of the vanadium, especially the vanadium-5 salts, was very low, if we went indirectly, we produced vanadium-5 from a more soluble form, we were able to get 2 molar. And 2 molar was sort of like this critical feature that we had to achieve in order to get an operating practical system. So we published another paper, and Martin and Tony and Bob Robbins were on this first paper on the vanadium flow cell, that we were able to actually demonstrate that it did work. Soon after, our Franz Grossmuth, who was here, he also joined and built our first flow cell, and testing various electrode materials, membrane materials. My husband Michael was actually really keen at the time. He used to work for the analytical laboratories at Lidcombe, and he was so excited. He thought, oh, we wanted to be part of this journey. So he applied to do a master's, and Tony Fain was his supervisor. So for the next couple of years, he was also part of the team doing his master's, but then continued on for many years later as part of our team. So by then, by about 1987, we had demonstrated that the flow cell could actually work practically. We were able to get a good reversibility, good efficiency, in fact, but it was only in a small cell, and high concentrations. We were able to get high concentrations. So the university came around, Unichem decided to do a feature on the vanadium flow battery, to put it into our local university magazine. And so we appeared in the magazine. And the next day, and they also issued a press release. But the next day, all of a sudden, everyone, as a result of this press release, we were contacted by television people, newspapers. They all came to the laboratory all of a sudden to do a feature on the vanadium flow battery, even though we only had a little cell at the time. And so we thought, okay, this is interesting. We'll probably be in the science section of the Sydney Morning Herald. But the next morning, my husband was really keen. He got up really early, went down to the newsagents, and he came back and he said, Maria, you're on the front page of the Sydney Morning Herald. And I thought, oh no, how embarrassing. This is embarrassing, because it was only a small cell. And so that article led to all these newspaper people, the news reporters from television. They came, were interviewing us. And Chris Bell, who was the head of school at the time, he came up, no, he was actually head of chemical engineering at the time. He came up into the laboratory, and after they finished interviewing me, he said, Maria, does this work? He said, it does work, doesn't it? I said, I hope so, Chris. So anyway, so that was, but I was feeling so anxious from that point on. I felt, we've got to prove that this actually does work, and that's what sort of drives you from then on to keep going and to achieve something, because it was, as I said. But soon after this article, we were contacted by Sir Agnew Clough from Agnew Clough Limited in Western Australia. They had a vanadium mine in Western Australia, so he saw that this could be a great market for vanadium. So he came to the university, he approached Unisearch, and he negotiated an exclusive license for the technology. This is back in 1987. And for the next couple of years, the company funded us. But sadly, Sir Agnew passed away, he had a heart attack, sadly, short time after. And then the company couldn't continue funding it because of the financial crisis in the mining industry at the time, so that the Agnew Club returned the license to the university. So the university was able to then look for other licensees. So just quickly summarising what happened from then on, in 1984 we did the first practical experiments that the flow battery would work. 1986, filed patents in Australia, USA and Japan, and at the time when we approached Unisearch about filing the patents, they asked us, where should we file? And we knew that it was very expensive to file patents around the world. So at the time we thought, okay, well, we're in Australia. We know Japan's doing a lot of work on flow batteries, and that could be a potentially large market. And the USA, of course, we need to do. We didn't file in Europe because we'd already published a couple of papers on the concept of the flow battery, and they're much stricter when it comes to patents, the novelty. You can't pre-publish. But as it turned out, a lot of the important features we hadn't published anyway. So we only filed it in those 3 countries, and they turned out to be quite the 3 critical countries at the time, although now things have changed. From 1984 to 2000, we continued extensive R&D, covering all different aspects of the technology, from all the different types of cell materials, characterizing and producing the electrolyte, stack design with mathematical modeling and simulation, fabrication, testing, sensors, control system development, all different aspects we had to, because no one else was working on vanadium flow batteries, and no one else was publishing anything at the time on vanadium flow batteries. So we didn't have to compete actually with anything, which is like what we have to do now. And then, because we were constantly getting more interest, commercial, and more publicity, we were continuously getting, even from overseas, magazines and newspapers were coming and interviewing us. That led to some interest from Thailand, where a company called Thai Gypsum, they were developing a self-sufficient, energy self-sufficient house using solar panels on the roof and a battery to store the energy at night time. They approached us and they entered into a license for Southeast Asia. And as a result of that, we did our first solar house project. We were very fortunate to get funding from both national and state government bodies. But in the early days, the interest was mainly for remote area power systems, because they couldn't really see the longer term applications. It was more for remote area power systems, so organisations such as NERDIC, ERDIC, the New South Wales Office of Minerals and Energy, the ARC. We were very fortunate in getting continuous funding, which allowed us to expand our group and bring in so many valuable people. As I said, so we initially, very early, in the early 1990s, licensed it to Mitsubishi Chemicals, Fukushima Kita Power Corporation, and Thai Gypsum, and eventually Sumitomo. So these are some of the photographs of the development of the stacks, where we're starting off with a small single cell, going to early small multi-cells, our first 1 kilowatt vanadium flow battery in 1998, our first 5 kilowatt in 1989, and here we see Chris and Rui, who are in the audience, and Rui is in the audience here, and our friend Jim Wilson, showing how we assembled the stacks. So these are some of the work, work that was going on in parallel to allow us to develop the stacks and build stacks. But one of the important features of the work, and very early on when we were approached by and licensed the technology to Agnew Clough Limited. So Agnew Clough, we were using vanadol sulfate at the time to make our electrolyte, which would cost about $800 a kilo. And because we were using high purity. And so Agnew Clough contacted me one day and said, Maria, it's not going to work. You've got to use vanadium oxide the cheap raw material. So he sent us a big barrel of vanadium oxide from their processing plant, their trial plants, and he said, you've got to get that to work. But of course, vanadium oxide doesn't dissolve, and that was one of the problems at the time. How are we going to make it to get it into solution to make it work? And we had Rod McDermott with us at the time. He joined Alpha a short time before. He was one of those handy people who would just try everything. So he got a beaker, put some sulfuric acid in it, put some vanadium oxide, put 2 electrodes in there, pass a current through there, and stir the powder to keep it suspended. This is something that you wouldn't think of doing, but he tried it anyway. And he came to me about an hour later, he said, Maria, it dissolved. So we thought, oh, wow, fantastic. So now we saw that there was a way of making the electrolyte from a cheap raw material, which is so critical to the commercial viability of any sort of product. So that led us to work out other ways of doing it as well, including, apart from the suspended powder electrolysis, chemical reduction, using sulfuric acid, oxalic acid, leaching it with V3, all sorts of different processes, and we filed a patent on that. And that was, again, one of the key developments that allowed us to continue working and get commercial interest. Other projects that we had to work on, in order to be able to operate the battery, we had to be able to monitor how it works. So one of the things that Michael did during his master's thesis was to investigate different ways of monitoring the state of charge during charging and discharging, so we could always know how fully charged or discharged it was. And he looked at conductivity. We found by monitoring the conductivity of the solution, we got a linear relationship between conductivity and state of charge, and similarly absorbance. So other types of methods that we were able to develop and demonstrate that you could operate the battery and know how to operate it efficiently. And again, we filed some patents out of that. That also then led to having sensors allows us then to develop more sophisticated controllers to be able to operate the battery. So we started working early on with Barry Madden, one of our lecturers in industrial chemistry, Rob Largent, Luke McDermott, Yifan Lee, and of course with my friend and colleague Jai Bao, continuing the work today on control systems. We did a lot of work on membranes. Back in those days, we didn't have commercial membranes that were suitable for vanadium batteries. So we had to look around for membranes that were being manufactured for different types of applications, and went through many screening studies, characterization, trying to work out develop methods to actually test the membranes and characterize them, and see if they would work in the vanadium battery. And if they didn't, if they were cheap enough, and one of the things that we found that, of course, the best membranes were always the most expensive ones. And we didn't want it. We were always conscious of cost, because working with industry early on made us very conscious of the fact that you can have the best technology in the world. If it's going to be too expensive, no one's going to take it up. So we're always conscious of cost, and we started looking at trying to take cheaper membrane or separator materials, modify those to see if we could get them to work in the flow battery and get the performance that we needed. Conducting plastics, that was another important development. In the early days, we were using very thick, heavy, bulky, and expensive graphite plates as our electrodes. We saw some work that was being done by a company that was developing zinc bromine batteries. They called it conducting plastics, and we thought, oh, what's this conducting plastic? So we started looking into it, and I was fortunate to get a couple of students who were very interested in polymers and plastics, and together with Rob Burford, we started looking at formulating, seeing if we could try and formulate some conducting plastic materials to make our bipolar electrodes. And then early on, we were able to also take some of these formulations and get batches made in 1 ton quantities. We were able to get into some of the commercial companies in Victoria to mix them, blend them, granulate them, and extrude them. So we were able to then make our graphite electrode substitutes using conducting plastics. But the graphite filters as well was also critical. As I mentioned before, one of the features that Elaine was able to demonstrate is you could get the best electrode surface in the world, polish it and make it really pristine, and it didn't work. So we discovered that different types of felts, which would form the electrode material for the reactions, some worked really well, some worked really badly. We thought, and the expensive ones were the ones that worked well. So we thought, okay, how can we take a cheap one and get that to work well? So we started studying it, and we found that the ones that worked well had certain oxide functional groups on the surface. The ones that didn't work well didn't have those functional groups. And in fact, they also allowed the electrolyte they made the electrode hydrophilic as well. So we started going through, I have a really good student, Björn Sund, and he started looking at all sorts of different ways of treating the felt to activate and generate those oxide groups. And that is now has formed the basis of all the manufacturing of the graphite felts for the vanadium flow battery. They use these activation methods that we developed, which shows that, you know, at different temperatures for a certain period of time, you could reduce this, get the minimum cell resistance and get the maximum performance. Looking at sulfuric acid as the concentrated sulfuric acid at high temperatures, or just thermal treatment. So then we started looking at the electrolyte as well, and we realized that the electrolyte worked in 2 molar solutions worked really well around room temperature, but if at high temperatures or low temperatures, one thing or another would precipitate. So we thought, okay, now, well, what can we do? How can we stop precipitation so we don't have to dilute the solution? We wanted to have a concentrated solution, not dilute solution to stop precipitation. So interestingly, I was actually teaching the Bayer process at the time to our industrial chemistry students in 3rd year. And one of the problems in the Bayer process is that you can't get the aluminium hydroxide to precipitate in the presence of certain organic impurities in the Bayer liquor. So I thought, okay, they needed to treat the Bayer liquor to extract the impurities so as to allow the precipitation to happen. Otherwise, the solution would stay super saturated and never precipitate. So I thought, okay, well, how about if we do the reverse? Let's try and see if we can find, in our case, additives that we can put into the solution to stop them from precipitating. And so we went through quite a few of our students, started testing. Faze is here today, who's one of our first students who investigated a lot of these additives, Chris, Michael, Nadeem, Asim, and we found, to our surprise, that a lot of additives worked quite well. So by having just, say 1% or a few, or 0.5% of things like ammonium phosphate or phosphoric acid, or things like that, we were able to stop precipitation and allow the battery to operate at much higher and much lower operating temperatures. So that's some features of the research. So, but as I mentioned, very early on, we were able to, and we were continuing this research over the years up until today, in fact. But in 1992, we managed to get our first licensee that wanted to take the vanadium battery and put it into a real demonstration. And this was in a solar house in Thailand. So the university signed a license agreement, and part of the collaboration was to build a battery at the university. They were wanting to open their first manufacturing or factory in Bangkok, and the Princess of Thailand was going to come and officially open this new factory. So they wanted to build a solar house and put a vanadium battery in there, and with solar panels on the roof, and have a part of the big celebration of the new factory. So within a very short period of time, we put with our team, Rui, Chris, John Chen, Jim Wilson, Michael, all of our team got together and built a stack, a 5 kilowatt, we started off with a 1 kilowatt stack, and then we built a 5 kilowatt stack later on. We had to use a lot of electrolyte, so we couldn't make a few test tubes of electrolyte. So Rod McDermott, with some of the other members of the team, put together a pilot plan so we could produce the electrolyte using an automated feeding and control. And we produced all the electrolyte in the laboratory. We built the stack, and our good friend Rob Largent, who's also here with us today from the photovoltaic group, he came and he helped us. He designed and built the controller, and that was critical too, because one of the things that we found in the laboratory we can charge and we can discharge continuously, and we can get really good efficiencies. But in a solar house, you charge the battery during the daytime, and it stays. And during the night, you might only charge it with a couple of amps. And if you're running the pumps continuously while you're only generating a very small amount of power, most of your energy goes into running the pumps. And we realized that the efficiency could be as low as 30% if that's the way you operate it. So we realized how critical flow control and the pump control was. And Rob Larger helped us to build a very simple flow controller, which would allow the pumps to switch on when the current was very low, would switch on for a few minutes, flush the electrolyte through, and then switch off until the voltage dropped again. So this was a very simple on-off controller, but it demonstrated the value and how critical the flow rate control was. And this is something we continue to work on today. So these are some of the photographs from the building and the demonstration. And then our colleagues from Japan came to the university, and that started a lifelong friendship. And our great friend, Dr. Sato, is here with us today. They were already working on iron chromium flow batteries at Kashima-Kita, but they realized what they saw, and Dr. Sato is going to tell us a lot more about it, but they were also generating vanadium as a waste product from their power station. And they thought, what can we do with this vanadium? And when they saw that they could put it into a flow battery, they got very excited, came and they licensed the technology, and that started a 5-year collaboration and friendship. And every time Dr. Sato would come out and with Mr. Shibata, we'd go to lunch, and he would also always order a VB, vanadium battery. So hopefully we're going to have some VB again this time. So some great photographs from the past there. We also did a project for the Australian Defence Department. They were very interested in the possibility of using flow batteries in submarines, where you could have the tanks forming part of the external walls. So anyway, so we did a project with them, and that worked quite well. And then the idea of the electric cars came along, because I'd been talking for quite a while and saying that if you've got a flow battery which stores all the energy in the tanks in solution, then really in the future you could drive into a refueling station and fill your tanks up with electrolyte, or empty out your tanks at the refueling station and fill your tanks with fresh electrolyte, and then just drive off. And so you would be able to, within a few minutes, refuel your car. And then at night time, when you've got spare optic electricity, you could recharge your solutions. So somehow this idea came up, and Bill Wentworth, who is the great-great-grandson of our famous explorer Wentworth, who went over the Blue Mountains, he knocked on my door one day, and he popped in and he said, I'm Bill Wentworth. I want to talk to you about your flow battery. So he was a real champion at the time for light rail in the city. He wanted to have, but not on tracks. He thought, well, there's no reason, we don't need tracks, we just need an electric tram like that running on batteries. So he was campaigning for quite a long time with the City of Sydney to run these sort of light rail systems in the city. Am I going past? Oh, sorry, I thought it was. Okay, so he used to come and visit me all the time. It was such a joy and exciting to see his enthusiasm and how he really loved the idea of there's a rechargeable, refuelable electric. Now, back then we were competing against lead-acid batteries. Lead-acid batteries were really the only commercial batteries available at the time. They had very low energy density, and their range was very, very low. So we could compete against lead-acid batteries, but not lithium batteries. So we sort of totally dropped the idea of electric vehicles, because in terms of energy density, you just can't compete with lithium batteries. But back then, everyone loved that idea. So these are some of the so we embarked on a couple of years program to build some vanadium batteries, and David Hogg from Unisearch at the time, he liked the idea as well, so he contacted one of the companies, go-karts, I think one of the companies that makes electric golf carts, And he got them to donate an electric golf cart. And that's what we were doing back then, because we had limited funds. And we used to just go around scrounging things for free. So to save money, or getting people to donate things. And they were usually very kind, and they would donate things. So we got this electric golf cart, and we built a battery. We built a duplicate battery that we had built and designed for the solar house. So it was actually oversized, but we stuck it on the back of the golf cart. And we were able to show that, yeah, rather than having a battery sitting on the bench and just showing a meter, sort of an experiment running and giving you a readout, we were able to show that it actually can run a car. So that was a really great demonstration, and that allowed us to host many visitors who were coming to the university during the time and go to a lot of exhibitions, and people would try the electric golf cart, and actually it was running on a vanadium float battery. So we enjoyed many exhibitions and international visitors in the 1980s and 90s. But in 1997, we were running out of funds. But then we were approached by a company in Western Australia called Pinnacle. And they were really excited and interested in the vanadium battery. So they negotiated, but it was a listed company. And they negotiated with the university. And being a listed company, they didn't want just a license, they wanted to buy the patents. So Unisearch agreed, and they sold the patents. And of course, as we all expected, Pinnacle couldn't do very much, because all they were doing all the time was trying to fight off takeovers continuously. Companies were coming on trying to take over the company, and in the end, a Canadian company called ERB Power actually took over Pinnacle. They moved all the patents offshore to Canada, and a few years later, during the global financial crisis, they were taken over by a Chinese company, Prudent Energy, and then the patents just ended up in China, and it eventually expired. So the moral of the story is, everyone rushes to file patents, but with a technology that takes a long time to develop, by the time the technology is ready to be utilized, the patents have expired. So that's okay, but now anyone was free to develop and commercialize the technology, and they weren't locked out. And that was one of the problems, because when Pinnacle and then VRV Power first took over the patents, they weren't happy and willing to give licenses to anyone. So that really slowed down a lot of the uptake and commercialization. But in 2006, the patent expired, freedom to operate everywhere. So from then on, a lot more work started going on around the world. But in 2005, we came up with a Generation 2 vanadium flow battery, which had new patents. So at the time, my husband Michael and a couple of other colleagues, and they said, we're going to do a startup company. So they approached the university, got a license to the technology. My two older sons came on board. They started working and developing the battery, Generation 2, at a company called V-Fuel. But we struggled. The market had still not developed, and we were just struggling to get any commercial investment interest in the company. So we had to, in 2010, we folded due to the lack of investment. But shortly after, it was only a few years later that all of a sudden energy storage started to become a big thing. So we started seeing in the early 2000s lots of commercial systems being set up and tested and demonstrated. In 2015, we actually even installed one of the early commercial systems in our basement downstairs. So during the breaks, you'd be able to go downstairs and have a look at one of these commercial units. Sumitomo Electric has moved on, and in the 2000s, they were able to install many different batteries in so many different applications. So we'll be hearing about some of these projects later on. But now, in 2003, for example, now we're seeing the spread of all the different vanadium batteries around the world. And we've now got hundreds of megawatt hours of vanadium flow batteries, and quite a few companies here in Australia setting up to install commercialised vanadium batteries here as well. This is the largest project in Australia, installed by Invinity in South Australia. Ronki Power in China have been doing enormous installations. They've got a bigger factory in Dalian, and their 200 megawatt, 800 megawatt hour battery is operating. But this is now, as we see this huge demand for vanadium batteries and vanadium, then we're starting to look at the availability and the supply of vanadium, which has now become a critical issue. And these are some of the forecasts of how much vanadium is going to be needed if we have a certain percentage of the future energy storage need from vanadium batteries. But Australia's in a good position. We've got a lot of vanadium resources, and hopefully we've got quite a few people here today who are part of the vanadium industry here in Australia. So hopefully they'll be part of the future solution to the supply of vanadium, and hopefully to make Australia a major supply of vanadium and vanadium batteries. So after 40 years, we're sort of finally maturing, and we've got so many people to thank and appreciate and acknowledge for all their efforts. And this shows some of the people from the early years, a lot of whom are here today, and all the names of all the people who have worked with us over the years. So we thank them all so much and appreciate their dedication, their enthusiasm, their passion and their commitment. So we thank you. This is 1988. This is my husband and the three boys. And there they are at the beginning of the year after all those years. And in fact, Anthony, who's here with us today, he actually grew up. He wasn't even born when we started working on the vanadium battery. So he grew up spending all his after school in my office waiting for me. Anyway, so thank you all. So we're going to move on with our program.